this one. So anyway, so using the R programming, I can make the 3D with the 3 lines of the code. Okay, very simple. Okay, and then the printout to the using the 3D printer. So a part of one of the tasks of your final project should be this one. Okay, so it's not the probably you did the project classroom project with the final term paper should be the paper side, or sometimes the report side, sometimes the poster. Okay, but this time you should do that, and in addition to that, one of the output should be data visualization using 3D printer. Okay, this is one of the example. Should be larger than this. So the main problem is not very difficult once you have the 3D data. 3D data means it's x, y, z coordinate value. That is called the STL file. So STL file. So if once you have the STL file, it's just the sending data to the 3D printer and print out like this. So
Can we see?
yes. So problem to print out that small size, 1 inch by 1 inch by 1 inch. Do you imagine how long it takes? 30 minutes. So when you print out the cigarette size, it takes 4 hours. So if you want this amount, for example, I have the geographical, the 3D visualization, it probably takes almost 10 hours using our printer. So the more expensive, the faster print out. But we have another high-end 3D printer in mechanical engineering, but I'm not sure whether we can use the scroll engineering. Try to. But anyway, format-wise, it's the same thing. So you need to have the 3D, the data, so the XYZ coordinate value. So if you have the graph style output, it's very simple to print out. But if you have the the histogram like that. So if you are using some existing tool or the commercial tool like I'm not sure whether you guys know the Origin. Origin is the software to make the bunch of various the graph tool. So it's a commercial tool, but at that time you can easily convert. And if you are using the MATLAB, so not very difficult to make the 3D data. But if you have just the image, but it's a problem to print out. But there might be software to convert the image 2D or 3D image to the 3D data. So anyway, do I have experience? No, that's the only one. We are going to try. So why don't you keep your mind? So when you evaluate, data visualization is one of the your output. One of the output. That's not the only one. Okay. So but reasonable size. So for example, if you are using the GeoVis that I introduced, the Google Vis. Google Vis have something that you can use a Google Map to show so at that time you can print out the 3D style. That will be much easier for user to understand your output, right? So 3D data visualization is one of the interesting area also. So unfortunately we do not have the color, so it's a single color. So but you can change the filament. There is a plastic like that. So, but unfortunately, right now we have only the single color that one. But I'm going to ask the multiple color. But that doesn't mean it's a color printer. So it has only the one, the extruder to the print out. So, but more expensive. The 3D printer has the support of multiple color. Anyway, it's for your experience. So I'm going to think the coordinate how to print out if it takes a longer time. So one day one team can use. So if you want to test right now, you can combine me or the Omar or I'm working with Z to test the 3D printer. So you can before the project you can test it if you want anytime. Okay. Any questions? Yes.
Professor, in the lab tomorrow, you asked the parameter setting you test. We have to decide. There is any restrictions for we have to set for the a priori
Which one?
algorithm? The a priori algorithm.
A priori algorithm? Yes, by changing the value, so you see the. Anyways, one of the main purpose of the lab 1 is get used to the existing tool. Okay, so it's not the programming; it's just using the existing software. Okay, so by changing the parameter value, so see the difference of the result. And as Hamud suggests, some of the data are not feasible for that. So try to find the feasible data set for the a priori. So it takes a time. But by changing, by filling some of the data, you can use the data set, you can use the software. Eventually know what does that mean, the support or confidence level. Sometimes each software use a different name of the parameter. Okay, so you can get used to such a thing. That is the main
We
purpose.
can generate more any number of rules.
Oh, yes.
The default is
Sure.
10.
Okay. Any other? So. The main problem of using 3D printer is it takes a too long time, and also it's the noise, and so once you start the 3D printing, you need to forget about. Okay, the last time that we have discussed about the clustering algorithm, the k-means and k-medoid. The difference between the k-means and k-medoid is the k-means use the centroid. Instead of the centroid, the k-medoid try to find closest the data. Okay, the others are exactly the same. Okay, it's a partition based. Today we are going to discuss about the hierarchical based clustering. Also, when you are doing the page 1, page 2, you don't have to worry about the data mining technique. Some of the students already decide I'm going to use this tool, this tool. No, you don't have to. It can be various way, different way. So that is a reason when you imagine your data set, be creative. Okay? If you search the Google like the data mining example data set, so probably you will get all the solution and even expected output. Okay? This is just the educational purpose, so we can turn. So next one is the hierarchical clustering. Hierarchical clustering. So its idea is simple. So there are two ways of the hierarchical clustering. So when you have the number of data item, if they are similar, we can merge. Okay. So for example, A and B are close, almost the same. We can merge into the A and B node. Okay. Then if D and E are similar, we can merge it, and that is close. C is close to with a certain criteria. Then we can merge it. Eventually, it will be one cluster. Okay, this is the bottom to up. Okay, in other words, it can call the agglomerative, the hierarchical clustering. On the other hand, divisive, the clustering is starting from the one data set. If you can find the group like AB is similar and CDE is similar, so we can bisect them, we can separate, and so on. Then we can eventually have a number of data sets. So there are two ways. The divisive is called the Diana. We will see the details of that. So Agnes is agglomerative, the nesting. It starts from the number of data sets. At that time, we should have the criteria, the rule, okay, objective function, whether they are similar or not. At that time, we can use a single link method and this similarity matrix. This similarity matrix means it's a distance. A number, the matrix consists of a number of the data item and a number of the data item. Then find whether this is connected, the similar or not. Okay? Then we can merge it, and eventually merge it, and finally we have the 1. So problem, we need to stop at a certain point. Okay? That is the threshold value. That can be the cutoff line. How can we find? That's a problem. So that is one of the drawbacks when we can stop. It's the same problem in the diagonal. It's a divisive analysis. So from the 1, so we can bisect, and when we stop, so that is the problem. So at that time, we can have the objective function. Objective function is we can use the same idea as the used in the partition based. At the time, we can consider the centroid or the centrality analysis, how much they are formed. So if we bisect, whether we lose some such a centrality objective function or not. So for this, the hierarchical clustering, we can use this kind of the dendrogram. So we can use it. We can build such a hierarchical dendrogram. Then user can select the level of the clustering. So we can cut this way, which means 1, 2, 3, 4 cluster. If we cut this way, it's a 1, 2 cluster. Okay, so that is the benefit of using the dendrogram for clustering. Okay. So there are different distance measures using such a hierarchical clustering, single link, complete link, average, and so on. So let's see the single link. Single link is the minimum distance. So let's consider 2 clusters. Suppose that we have the 2 clusters. Between the 2 cluster, distance between this one and this one is the minimum distance. The minimum distance for this one and this. Okay. However, the single link cannot represent overall the distance between the 2 clusters. So to address that one, we can also, there is a complete link. Complete link is the maximum, longest distance. For example, this one to this one, I'm not sure, this one to this one. So longest distance, that is a complete link. So they cannot, the single link and complete link cannot represent overall the distance between 2. So we can use the average. It's the all distance between 2 elements, 2 items from the 2 cluster, then average them. So, however, it takes a long time to compute all the cases. So we can use the centroid, so like x in this cluster, x in this cluster, and distance between 2 clusters. But as we have seen before, it's not the sensitive. It's sensitive for the outlier if you are using centroid. And medoid, you select to address the problem of the outlier, the extreme value, so we can find the closest value from the centroid. For example, in this case, this node will be medoid. We can use the distance between this one and this one instead of the centroid. Okay. So these are the distance can be used. That can be used for the hierarchical clustering. And then we can calculate the radius and diameter. So radius is the average. This is average of the square root, the distance from any point of the cluster. Okay, so you can. In case of the circle, it's ideal circle is a radius, and the diameter is all pairs of points in the cluster. This is from the centroid. This is from the 2 points. So eventually, this one represents the diameter. So over average the length from end to end is average. In ideal case, the circle case is diameter. So this one is a radius. Okay. So we can use such a thing. There are the variation of the hierarchical clustering. Okay. First one is the Birch algorithm. It's a balanced iterative, the reducing and clustering using hierarchy. So let's see the example first. we are going to use the three features of the each cluster. That include the first one is the number of items, for example 1, 2, 3, 4, 5. Second is the linear sum of endpoint x and y. Okay, sum of x, sum of x and sum of y. The last one is the square sum. It's a square sum. It's a square. So for example, this is a 1, 2, 3, 4, 5, 6, 36 plus 49 plus something like that, and sum of them. So it's kind of first momentum, second momentum in terms of the calculus. It's kind of momentum. So to describe the cluster, okay, it has the 5 point and the first momentum and second momentum of the data. This is called the clustering feature. Then we have this is the data, and this is the clustering feature CF of this data set. Okay, then we can build a CF tree like this one. So CF tree has each tree has the number of the cluster. So we can start from the 1 CF and try to separate by the so Birch is kind of the divisive the algorithm that can represent so there might be the rule of the parameter threshold. So it has a threshold value, so maximum diameter of the subcluster. So we can calculate from each the cluster, the subcluster, when if we divide into the group. So it has there's a maximum, the number of the children node. So by considering maximum, so we can calculate the diameter of the subcluster. So to maximize the diameter of the cluster, which means the children node, the lower level of the cluster, we can divide until we do not have the children node. So criteria is we are going to consider CF and such a threshold value. This one, the cluster diameter is same as the diameter, but it's divided by the n minus 1, because we are going to consider n times n minus 1. The distance is kind of average. Okay. So diameter is if the diameter is a maximum, it's bigger than the maximum diameter, we split until less than the maximum. Okay, that is a criteria. So we keep the certain the size of the diameter of the cluster. The camera is there might be, oh yes. This slide shows the overview of the camera. So if we have such a, for example, graph data. So graph data, we start from the click. Click means it's if the nodes are connected each other as much as possible, this is called the click. So if you have this one, this is not the click, because this one is not connected. So if this one is connected and connected, we can say this is the click. Okay? So we can find as many click as possible. It doesn't have to be this one. Okay? So this may be the click. Yes, this one is also click, but as you can see, if the two ends are connected, so that is a click. So we can find first as many click as possible. Then we are going to merge. So it's the agglomerative approach. So we are going to merge and until the certain criteria. Okay, so at that time we can consider relative closeness, and which I do not clearly understand. I never used this one, but it may be the certain criteria. It is based on the first we find the collect of the basic unit of the graph, subgraph, then we are going to merge the up to by considering the relative closeness, whether two clicks are close, the similar or not. If they are considered as a similar one. So for example, this is the original graph. So you can imagine that this one, this one, this one, there might be three groups, right? So this is our goal, the ground truth. So to find such a three group, we can start from the clicks of this one. Then we will find whether these two clicks are similar using the relative closeness. So relative closeness is by counting the number of the distance, okay, and the number of the node that form the click, okay. Then it's kind of normalizing the two cluster size, okay. It's kind of relative the distance. So idea is whether this one and this one, this one, this one. But if the node is big, so we should normalize such a relative distance. That's the idea. So if they are close, then we can merge. So eventually we can have this one, this one, this one. Why these two are not merged? Because it's connected through the only two of them. Okay, so that is the idea. Why do we start from the click? Because they are connected each other. So we can start from the clicks, such a connected the small subgraph. That is the chameleon. So we can apply such a chameleon to the image clustering, okay, which is called image segmentation. It's a very important task in image processing. Also, we can consider the probabilistic, the hierarchical the clustering. So at the time, we model each cluster. Okay, as for example, in this case, we are going to use the Gaussian distribution. So this is a model-based. Model-based means we design our cluster. The cluster from the Gaussian distribution. Okay, that's our model. Then try to find the best fit, best cluster that fit to the Gaussian model. That is the idea of the model-based generative model. If you are seeing any model-based or generative model, that means it's a statistical model. You can use the different distribution like the chi distribution or the exponential distribution, but 99% they are using Gaussian distribution. The reason is that it's based on central limit theorem. Central limit theorem, which is one of the important statistical theorem. Idea is that if you are using I forgot the name of that. When we are saying the px, what is the x?
Probability. Condition. Element.
Why I cannot remember. What? A random variable. The random variable. So, for the random variable, if we order the random variable, then that will form, if we have the usually empirical result shows, if we have more than 15 data item, then if we order by the random variable, if we reorder the random variable by the occurrence, it will form like the always Gaussian distribution, no matter what types of the model you have. So that is true. Think about it in common sense. If something event is frequently happen, it will be from the middle. Then some of them are rarely happen. Positively happen and negatively rarely happen. So anything, actually if you reorder them, it will form the Gaussian normal distribution. So that is the idea. Okay. So using that idea, we can use the Gaussian distribution to find the parameter value. Why? Because the Gaussian distribution can be described by average, mean, and variance. Okay? Average is the middle, and the variance is how much wide. Okay? The shape of the distribution. So the benefit of using such a Gaussian distribution is we need to find only two parameter value to find the cluster, because we assume each cluster form the Gaussian distribution. So how can we find such a parameter value? At that time we can apply the likelihood. Likelihood is the kind of the process function to find the parameter value. How can we find? We can product n number of the data item or the n number of the data by applying such a value, then the product, then we can find such the parameter value. That is a likelihood. Because that is the product of the two huge numbers, especially the exponential part. So mostly we use the log likelihood. If we can set the log, then we need to remove the exponential, then it will be much simpler. So using the log likelihood, we try to find the argument of mean and variance that maximize the likelihood function. Okay? That is the idea of the model-based approach for that hierarchical clustering. So we design, we model each cluster from a Gaussian distribution. Then apply log likelihood function to find the parameter value. Okay? That is the idea. We will see another example of the model-based approach in the advanced clustering algorithm. That is called the EM clustering, expectation and maximization clustering algorithm. So this is a visualization of the Gaussian distribution. So if we can print out this one using the 3D printer, that will be the 3D data visualization. So this is one of the example of the two cluster. There are two Gaussian distribution. So if we at that time we need to find how many means, two means and the variance. We will see the more example in the EM clustering algorithm. I'm going to skip this part. Density-based clustering can be used for the graph-based approach. What does that mean is, if they are, idea is, if the data are dense, not sparse, dense means form of cluster. Otherwise, if they are sparse, they could not form a cluster. That's the idea. So, can we define whether how much they are dense? So at that time, we can use the two parameters. One is the EPS. It's the maximum radius of the neighborhood. How much we consider this amount or this amount? So that is the maximum. The EPS is the maximum radius that we are going to consider whether this one is called the cluster one. Minimum point. Even though these two are dense. Here, 2 point. Can we say that this is a cluster or not? So you can set up the minimum 5, for example. So at least the 5 points are dense within the EPS, the size of the cluster. Okay. At that time, so we can say the N EPS means the number of the set of the neighborhood, okay, whose distance is less than EPS. How many of them are within the, for example, in this case, the EPS is 1 centimeter, like this one, and the minimum point is 5, whether this one, within this, whether they belongs to the D, okay? So distance should be less than the EPS within this one, and number of Q, the data point P that are close to this one. Okay, so that is the neighborhood of the Q. Okay, and at that time, if directly density reachable means, if we can, so from Q we can find the neighborhood of the EPS, which means it's a dense. It's satisfied with the two conditions, EPS and minimum point. Then P is, for example, is also the neighbor. You can find it satisfies the 2 points. Then at that time we can say Q and P are reachable. We can this point and this point, they are reachable if the P is directly density reachable from point Q. So because they are belongs to each other, okay, and they are the neighborhood, number of neighborhood is bigger than the minimum point, okay, which means we can find such a neighborhood of the P, neighborhood of Q, and neighborhood of P. That means we can make the P and Q belongs to the same cluster. So we try to find as long as possible reachable, directly reachable point. Okay, so that shows this one. So for example, the P and Q using this point, this point, this point, this point, Q and P are reachable. Okay, so density connected, which means we can say all of these points form one cluster. Okay, it's a density based. That is the reason it's called the density based. So it's called the density reachable. So we can find as many points as possible that belongs to the cluster. At this time, this one does not satisfy with the minimum point. At that time, we can say this is outlier. Okay, some of the points are end of the cluster. This is called the border. And some of them are in the middle. This is core point. It's kind of centroid and something like that. Then we can apply this even in the image segmentation. Let me show the example of the demonstration